Hi. So we've seen how to make this next token predictor into a useful assistant using SFT, where we still minimize the same cross entropy loss per token, but then we use a different data structure, right? How we format our data into the context, prompt, and answer triplets. Then we briefly looked at RL. We looked at the reward function. We looked at the value function, also sometimes known as the critic. And we looked at the LLM itself, which sometimes they call the policy network, right? So what did we learn? We learned that, okay, the reward function itself is almost the LLM, where we change the output linear head with this reward. Similarly, for the value, you again have to use the same LLM, but now instead of finally predicting the reward, we predict the value for every token, and we want this to be the average reward until then. And now we want to look at some pitfalls and advanced RL. So there is this thing called as reward hacking and overfitting, and this is based on Goodhart's law that when a measure becomes a target, it ceases to be a good measure. And this is valid not just say in LLMs but even in life, right? When we focus on metrics such as citations or H index and forget about like core research itself, or care about, let's say, just revenue or app download and daily active users, but forget about, let's say, the business itself. And even in health, we may care about metrics such as number of steps and so on, but we forget about like the core health itself. Similar is applicable in LLMs. So what happens in LLM is that the LLM learns to kind of output very flowery language such as maximum praise, eloquent, excellent, flowery words, adoration, and so on. And with this, it starts to kind of get higher and higher rewards, and then it completely breaks apart. So what happens is, in the SFT stage, it starts to output something which is coherent, it's clear, articulate, and demonstrates language understanding. Then after a few steps of RL, if you're not careful, it starts to be a bit repetitive, and then finally we get a collapsed model where it just outputs junk. So from overfitting, it goes to reward hacking. And what we want to do is prevent this. And one way to prevent it is by saying, okay, you cannot drift too far from where you were. Right? So after SFT, we had a decent model. RL, we don't want to, change it too much. And how can we do this? Well, one way to do this is by saying, okay, the KL divergence of my current model to my previous model should not be very high. Yeah, and you define KL divergence like this. So the KL divergence between my current model, pi naught, and pi 1 is essentially this formula. And we want to keep this small. We want to keep this KL divergence small to prevent collapse. So this is one algorithm that was called TRPO, Trust Region Policy Optimization, which was proposed by Shulman et al. In 2015. And what it does is it kind of does exactly what we discussed previously. It says that, so this is our advantage function A, which is the reward minus the value function, and earlier we were just using this to kind of weigh our cross entropy function. But in addition to that, we now have this KL divergence term. And in a sense, you can think of this as, let's say, a regularizer. If you remember our regularizer from, say, our so we have, let's say, our cross entropy loss between our output and target, and then we have this regularizer. And what does this regularizer do when we want to train our usual, let's say, neural networks? It says, okay, I don't want my weight values to be too high, so I want to penalize with that. Similarly, here we want to say that, okay, I don't want my KL divergence to be too high, and so I want to penalize with that. So if you get too high, then my loss increases, right? My penalty increases. And it's in some sense, so I want to maximize my reward, but I don't want my model to change too much. And this is this constraint optimization, and we do this using importance sampling and so on. So TRPO kind of set the idea, but it wasn't, let's say, practical for LLMs. Why? For a 70 billion LLM, you would have 4,900, parameters in 4,900 billion parameters, so 4.9 trillion parameters in our Hessian matrix. So it's not possible to kind of use TRPO because it uses second order, let's say, calculus, second order terms. So we came up with an approximation to this, and in the approximation, we do exactly what was proposed by Shulman et al. In 2015, but by kind of doing it in a hacky way. So what they were saying was, okay, you may optimize a reward, but you will incur a penalty if your model changes too much, if your KL divergence is high. Yeah, and so this is what is saying that my total reward is on a balance. So you want to maximize the reward while you still want to minimize your KL divergence penalty. So if the model drifts too far from SFT, penalty grows and it pulls it back. By the way, this RL step is also called alignment, right? Because you're aligning your model with, say, certain rules, certain data. Now, the first time it was really used properly was a PPO, proximal policy optimization in RLHF. And so, like you remember, RLHF is a framework and you can use reinforce, but now we want to use PPO, proximal policy optimization. And in proximal policy optimization, they kind of do this KL divergence, but in a shortcut, and we will discuss how. So what they say, so Shulman et al. Then in 2017 said, just clip instead of that constraint where you have to do importance sampling, where you have to create that distribution and then compute the KL divergence between the original model distribution and the current model distribution, because that's just too expensive and cannot be done in the realm of LLMs. So this loss, again, it looks fancy and complicated, but it's not, trust me. So all this is saying is, okay, we have our advantage function, which is your reward minus value. And now we will have, a ratio of pi 1 to pi 0. And it's important to understand this, at least at an intuitive level, why we are doing this. It's essentially saying, so when we create data in batches. We create data using pi naught, right? But now we have made, let's say, a small update in our LLM. We have changed from pi 0 to pi 1. And now we should ideally recreate data using pi 1. But since we are not doing that, we kind of multiply it with this ratio. And what does this ratio do? Let's say pi 0 was already good at something. Let's say a quick brown fox. It was already giving us jumps, and our reward model gave, let's say, 2.0 for jumps, and then we moved more in that direction. And now, because our model wants to output jumps even more because it got a higher reward, like our pi 1, and now let's say it has a 4.0 reward when it outputs the same jumps, right? So we want to divide this 4.0 by 2.0 to get a final 2.0 to multiply with our advantage, instead of using that original 4.0, because we have to kind of compensate for this tail data. Yeah, so we're saying, okay, we want to compensate for that stale data and have that advantage, but I want the minimum of this, my current advantage, and this, this 1 minus alpha to 1 plus alpha times a. So if say my not alpha, sorry, this epsilon. So if my epsilon is 0.2, my 1 minus epsilon will be 0.8 and this will be 1.2. And then let's say this is some ratio 2.0, right? So it'll be this minimum of all these things, right? So I will have, say, 2.0 of my advantage, 0.8 of my advantage, and 1.2 of my advantage, right? So it will kind of make sure that even if I want to go all the way here, let's say using my original 2.0, it will clip it. It will say, okay, I will only allow you to get till the end of my circle here. Yeah. So this is all that there is in PPO, in proximal policy optimization. And this proximal policy optimization was used by GPT, by a lot of LLMs before, let's say, things change with DeepSeek. And we're going to come to that. But let's say, what is the headache with PPO? Well, there are major headaches with PPO. We have to have 4 models simultaneously in GPU, in memory, and we have to go through each of them to be able to finally compute our loss with which we update the LLM. What are those models? Our value function V, which is also called the critic, which can be, let's say, 7 billion parameters. Our reward function, which is again 7 billion parameters, right? They're all copies of, so the LLM is initially copied into the reward function into the value function. And then we also need the reference policy, right? Which is another 7 billion. This reference policy is our pi naught. And then this is our active policy. This is the current LLM that we are actually optimizing, that we are actually training. So to train this one model, we need the other 3 models. There may be a small optimization where we may have just 2 different heads for the reward and value, but still you get the point, right? We still have to have at least 2 to 3 full LLMs in memory before we can optimize that 4th LLM that we are actually interested in. And this is backwards. This is super inefficient, and training LLMs is already difficult because you have to have so many different GPUs even for a smallish model, and now this just makes total memory very, very high. So what can we do? So DeepSeek R1 came up with this brilliant idea. Remember that average reward that we were worried about? These GPO people, Shao et al. In 2024, kind of just turned it around, and it's brilliant what they did. They said that, okay, so this is my V, right? I'm interested in my R minus V. So they said, okay, why don't you make your V just an average of different responses from the same LLM for the same prompt? Right? So you give the LLM the same prompt, maybe 8 different times, you get 8 different answers, and you just average all of them and call it V. And this was brilliant. It works perfectly. And then the PPO loss, you just change the advantage function, and this terms remains exactly the same as PPO. So same as PPO, but it is group relative, and there is no additional model needed. Right? Because you are then going over all your tokens, all your groups, let's say 8 of those responses that you cared about, and then over the number of questions that you have in your batch. And this is why they have this queue. And we kind of explain this using this diagram here. So we don't need this critique model. We don't need that V model, and that simplifies training a lot. So what we are doing here is, it generates these 8 different responses, and some get, a good, so some get penalized and some get reinforced. Some get penalized, some get reinforced. And then the V is just an average of that, right? 1 by G, sum over 1 to G of those rewards. So brilliant idea, so simple, right? And now we use it all the time. And we will see this in code, but it's also brilliantly simple in code, right? So in code, I'm going to show this to you using a math example. So the math question that we want to solve is using this Qwen 2.5, Qwen 2 0.5b math reasoning model, and we're going to apply GRPO to that. And what we are going to solve for is, we want to solve for this equation 2x plus 5 equals 15. And now the 2x plus 5 equals 15 is going to give us, we will run this same thing 8 different times, and then it's going to give us some 8 different answers. And we're going to look for 2 different things in those answers. One, we're going to look at, does it have these think tags, right? You see these think tags or not, right? So it's think and then slash think. right? So we want it to think, and this is why we wanted to have those think tags. And finally, we will look at the final answer, right? So this is also that final answer. So 2x plus 5 equals 15, 2x equals 10, x equals 5. So we will also look for that final answer, right? And now let's look at what it looks like in code. And it looks, I mean, really simple. So we import a bunch of things. We format our regex. So the regex looks for those think tags. And then this is the accuracy of the reward, right? If we got the correct answer or not. And then we just need to set up our config and trainer. And that's it. And what is brilliant about, math or coding models is that you don't need a LLM for a reward model, because these are, a structured world. You know what the answer should look like. You know exactly what the answer should look like. If it's code execution, you know. If it is math equation, you know. And this is why you don't need a reward model for this. And this is why we do so well in coding, right? Because it's such a cool way to get a reward. This is something that you should know. And then finally, after GRPO, came DPO. So DPO came in actually it came before, and this was used by models such as Llama and Mistral and so on. And in practice, models actually use a sequence of all these, all the way from SFT to PPO to GRPO to DPO. And I'm going to talk about this in the next section. So in DPO, again, it's a little bit hand wavy, but essentially what they said was, and there's some very interesting algebra, and it's actually mathematically equivalent to PPO plus KL penalty without doing that. It's just saying that, okay, this is my sigmoid function, this is the ratio of my, policy network, which is our LLM, for the current model to the previous model, and W are the winners, L's are the losers. W's are the ones that we chose, the humans chose, and L's are the ones that humans rejected. And so L is the preferred response, L is the rejected response, sigma is the sigmoid function, beta is just a hyperparameter temperature. And we're just saying that, okay, in this DPO, we're going to minimize this contrastive loss, which is just the difference between our winners and the losers, right? You want to push the probability of the winners up, and you want to turn the probability of the losers down. So no reward model needed, no PPO needed, just this clever algebra to reparameterize, just the preference pairs. And DPO in code is again very simple. So we are going to see this in code later. But here you see that I'm just going to look at, we're going to create this data using our, so the DPO data is just our, prompt. And for that given prompt, we want to choose our winners and losers from our data set. This data set is also from Hugging Face, but a lot more on that when we actually do the code walkthrough in the end. And then, like usual, we set up our config and our trainer. And that's it. That's all that there is.